Howdy. I'm Frank Brown Bear, standing in for Mr. K today. He couldn't bear to make another video. So let's get started. We're looking at definite integrals today using the fundamental theorem of calculus. So fundamental theorem of calculus tells us how to evaluate an integral. So if we took a look at this integral right here, okay, this is a definite integral because it's got a lower and an upper bound. So you integrate it like you would normally, all right, but you don't have to worry about the constant c because you have the two bounds. So here's our integral. I rewrote it as x to the 1/2, and then when I integrate it, I add 1 to the exponent, and then divide by that new exponent. And then I just rewrote this as 2/3 x to the 3/2. Now, this notation here just is a notation that we use to show how we're going to evaluate it using the fundamental theorem of calculus. All right, so what you do is you substitute in your upper bound, which was 3. So we did that math right here. And that is equivalent to finding the area, the net area under this curve. This is the curve of the square root of x. All right, then we plug in the lower bound into it, and that would be the same as finding the area under the curve from 1 to 0. So if we take the area from 0 to 3 and we subtract the area from 0 to 1, then we're going to be left with the area from 1 to 3. That's basically what the fundamental theorem of calculus is telling you. So that's the geometric explanation of why this works. Now, I put a link on Google Classroom that you can do the very same thing. So I'll just show you how to use it here real quick. All right, so you can just type in your whatever the equation is right there. So I'm going to do square root x. And then I use these two sliders as my upper and my lower bounds. Okay, so our upper bound was 3, lower bound was 1, and there's my area. So we call this, and when we're doing an integral, this area is known as the net area. And we'll talk about why it's referred to as the net area under a curve. And it has to do with if you've got some area that is under the x-axis. But that's how you can use Desmos to do it, to see it at least graphically. All right, so our next example here was find the area under the curve, or the net area, or integrate this, I'm sorry. So when I integrate that, I'm actually calculating the net area under this curve. So that curve is a parabola. It's shaped like that. So we did a normal integration of x squared and of 2. And then I evaluate that from 1 to 3. So I'm integrating from right to left here. The way that you do that, though, is you substitute in the upper bound first. So there's the math for that. So that would be 3 cubed, 27 divided by 3, 9. That's 6. So 9 plus 6. That means the area under this curve is 15. Okay, then we're subtracting the area from, so that's the area from 0 to 3. And then we cut away the area from 0 to 1. Okay, so that would be 1/3 plus 2, so that's 2 1/3. All right, so I subtract off the 2 1/3. That's the area from 0 to 1. And when we do that, we get 12 2/3, and or 12.66 repeating. So that's a definite integral using the fundamental theorem of calculus. All right. So on all of these examples, I said anytime we're talking about integrating, we're talking about the net area. Okay. So this is the net area under this curve. Got a little chopped off there, but the curve here that I'm showing you is 4x minus 4 times the square root of x between 0 and 1. So this portion, here's 0, here's 1. Here is the area that is bounded by that curve and the x-axis. So when we do the integral for this, we're going to end up with a negative value. So when we talk about area, area can't be negative. It wouldn't make sense. The negative just indicates that the area is under the x-axis. Otherwise, yeah, that's all the negative means. So let's take a look at this. We're going to integrate it. So I'm going to rewrite that 4 root x as 4 to the x to the 1/2, and then I'm going to factor out that 4. So this integral, now we call it a definite integral. And then that 4 is a constant, so I can pull that out front and integrate x minus x to the 1/2. All right, now let's go ahead and integrate that. All right, so the integral of x is going to be x squared over 2 minus, and then the integral of this is going to be, I'm going to add 1 to my exponent and then divide by that new exponent. And then I can rewrite this as x squared over 2 minus, when I'm dividing by 3/2, that's the same as multiplying by 2/3, x to the 3/2. And I'm going to now evaluate that from 0 to 1. But remember, I have that 4 out front. So when I'm done evaluating this, I've got to multiply that by 4. So I'm just going to put the 4 there so I don't forget. All right, so I start by plugging in my upper bound. I'm going to have 1 squared, which is 1/2, minus 1 to the 3/2, which is just 1. So that's 1/2 minus 2/3. Okay, so that's substituting the 1 in. All I did was this. Now when I substitute the 0 in, well, that's going to be 0, and 0 to that is 1. Okay, so we're going to have, this would end up being 0. And then I've got 2/3, 0 to the 3/2, okay, which is just 0. So that all just turns out to be 0. Okay, so now I just simplify this all, get a common denominator, 6. So this would be 3, this would be 4. And I'm going to have 4 times negative 1/6, which is 4 over, negative 4 over 6, which is negative 2/3. And that would be the value of this integral, negative 2/3. Okay, and The negative is just indicating that it's underneath the x-axis. So when we have a combination, the first two examples, everything was above the x-axis. So we didn't really, the word net really didn't matter because you didn't have any negative areas. Okay, the third example was purely negative, just meaning it was underneath. So net area has to do more with if you have a curve and the interval that you're integrating over has portions that are above the x-axis and portions that are below. So in this case, the one on the left here, you can see that the red area is greater than the blue area, so the net area is positive. Here, the positive area is smaller than the negative area, so our net area is a negative value. So you just got to keep in mind when you're integrating, you're finding the net area. If we needed to find the total area, what you would do then, depending on... All right, our next example 4 here, now we've got a combination of finding the net area because we've got some areas that are above and some areas below. And the question is asking us to find what is the area of bounded by that curve and the x-axis. Make that a little bit bigger here. We zoom in on that, gentlemen. Yeah, thank you. Yep, there we go. That's better. Okay. So we're going to find, the question's asking us to find the area bounded by that curve that's between pi over 4 and 7 pi over 4. So we do our integral, and then by the fundamental theorem of calculus, we take the upper bound, plug it in. That would be finding the area from 7 pi over 4 all the way back to 0. That's this whole thing here. And then we're going to find the area from 0 to pi over 4 and subtract that from this, and that gives us our area that we're looking for. All right, so when we integrate sine, we get negative cosine. When we integrate cosine, we get sine, and I'm finding the intervals pi over 4, 7 pi over 4. So down here is 7 pi over 4. So you can see root 2 over 2 is our cosine, negative root 2 over 2 is our sine. So when we evaluate this, this gets put in first. So I would have over 4 plus sine 7 pi over 4 minus, and now I put in my lower bound, okay, that's how we're going to evaluate it. Okay, so cosine at 7 pi over 4 is root 2 over 2, but that makes it negative. Sine at 7 pi over 4 is negative root 2 over 2. So when I add those up, and I end up getting negative root 2. Okay, and then over here, okay, at pi over 4, cosine is root 2 over 2. Okay, that makes it negative. Sine is positive root 2 over 2. So those become 0. So then this whole part is just 0. And I've got negative root 2 over, or root 2 minus 0. So my net area is negative root 2. And that kind of makes sense because there's more negative area than there is positive. So the net is going to be negative. All right, the next one, you're given integrals and you're asked to use those to figure out this final integral. So I drew some pictures to help visualize this. Okay, our first integral is from 1 to 3 of some function f of x. So that's this red function that I drew here. Okay, so from 1 to 3, that area under that curve is equal to 2. All right, now if you take that same function and we calculated the integral from 1 to 6, these two values right here would add up to be negative 3. So then the question is asking you, what's the integral from 3 to 6? So that would be this area that's labeled with x. All right, so we know that when we add these two values up, the net area between 2 and this negative area that we'll say is x has to be negative 3. Therefore, that area under the curve, or between the above the curve but below the x-axis, has to be negative 5. All right, next one. Okay, so this is, we're given these intervals from 0 to 2 of the same function, 4 to 6, 0 to 6, and we want to find 4 to 2. All right, I can take these three intervals and add them up, and they're going to have to be 0 to 6. All right, so this first interval is from 0 to 2. Then the interval that I'm looking for, this one starts at 2, is 2 to 4. That's the one that we want. Then my next interval would start at 4 and go to 6, which I know. And then this would be equivalent, this would be the same as starting at 0 and going all the way to 6. So now I can just substitute in those values. So this is 5. Don't know what that is, so we'll just call it x. This is negative 2, and this is equal to 7. So that missing integral would have to have a value of 4. All right, to wrap it up, example 7, you're given this integral and you're told that its value is negative 4. And then use that to determine these other values. All right, so first one is just what's the value from, if this is negative 1 to 1, all right, and you switch these, our rules of integrals say that this switches. All right, so this is going to equal, because these are in the opposite order, so this becomes positive 4. All right, now on part B, we can take this and break it up into two integrals. So this would be negative 1 to 1 of 2 plus what we were given, f of x. All right, we know that this is negative 4. Now we're going to evaluate this. So the integral of 2 is 2x, and I'm going to evaluate that from negative 1 to 1. Okay, so that's going to equal 2 times 1 minus 2 times negative 1 minus this 4. So that's positive 4 minus 4, and that's equal to 0. All right. Here we can use our constant rule. We can pull that constant out front and then do the integral. So we know that our integral of this is equal to negative 4. So our integral is negative 8. Okay, so here you're given the value of the integral, k, and once you integrate that, you get 7. So we know from just like back in example C there, that we can pull that constant out. All right, we know that this value here is negative 4. So k times that integral has to be 7. So there's our value of k. Okay, guys, that wraps it up. You guys have a good weekend. It was nice teaching you today, and probably Krolik will be back on Monday. So have a great weekend. Take care. Bye-bye.